right, section 4 of chapter 14, colligative properties of solutions. So colligative properties, what are those? Well, let's figure that out. So what the heck are they? Dun, dun, dun. All right, they're properties, physical properties of a solution that depend on the number of solute particles, but they don't care what those solute particles are. That's a really important thing, and it's kind of a funky thing. So it doesn't care if it's like glucose dissolved in there, or if it's, I don't know, benzoic acid dissolved in there, or sodium chloride, you name it. Like, it doesn't care. It's just like, how many particles are there? That will affect these colligative properties. So on that note, a mole of a soluble molecular compound, that will only make 1 mole of particles. So if I have, let's go to like sucrose. If I take 1 mole of sucrose and I put that into water, I get 1 mole of sucrose molecules floating around in my water. If I take an ionic compound though, right, put an ionic compound in there, I'm going to get more than a mole. So 1 mole of sodium chloride, right, that's going to give me more than a mole of particles. Why? It's because ionic compounds, soluble ionic compounds, they dissociate. Those ions come apart, right? Sodium chloride, when that dissolves, I get sodium ions and chloride ions. So 1 mole of sodium chloride actually gives me 2 moles of particles, right? I get 1 mole of sodium, I get 1 mole of chloride. So it's like, boom, it doubles up. If I had something like magnesium chloride, right, MgCl2, that would give me 1 mole of magnesium and 2 moles of chloride. So that would create 3 moles of particles. So ionic compounds have a much stronger effect on these colligative properties. All right, so you're probably just chomping at the bit, like, well, okay, what are these properties? All right, so again, they depend on the number of soluble particles. They don't care what the particles are. Let's get to it. All right, come on, click. All right, so we have vapor pressure lowering, boiling point elevation, freezing point depression, osmotic pressure. I'm going to do osmotic pressure just in class with you guys. I'm not going to include it in the video here. And we're not really going to have any problems on it, on tests or anything. So don't worry about that too much. Let's talk about these top 3. Right, so if I have a sample of water, a glass of water, a beaker of water, if I'm being all sciencey, right, that water has a vapor pressure, that water has a boiling point, and that water has a freezing point. But if I put something into that water, anything that dissolves in the water, if I just dissolve anything that'll dissolve in there, all right, so now I make a solution, the vapor pressure is going to drop, the boiling point is going to go up, and the freezing point will go down. All right, so these properties change depending on how much stuff you put in there. So the more stuff I put in there, so if I put like another scoop of that solute into my solution, the vapor pressure drops even more, the boiling point goes up even more, and the freezing point drops even more. So let's go over those now. Let's kind of see what's going on. All right, recapping things. Vapor pressure, you guys should know what vapor pressure is. Anytime you have a liquid, there is a small fraction of the particles that have enough energy to break into the gas phase. Also, they would probably also need to be on the top of this thing. All right, so you're not going to break out to the gas phase from way down here. But anywho, so it creates this vapor above here, and that creates this vapor pressure. When I put something into this, all right, so I dissolve something. So let's just say this is water, and I dissolve something in here. Let's say I put in some methanol. All right, boom, 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 boom. Those are all my methanols in there. And I create this solution. All right, typically the solute solvent attraction is stronger than the attraction just between solvent and solvent, right? So this attraction is stronger than this attraction. So this guy's going to be even less likely to take off and go in the gas phase. It's like, no, don't leave me. I'm your friend. And so it's like, it just doesn't want to go. So it stays there. That's like one reason for vapor pressure lowering. There's another reason I've also heard, and that's if you think about when this thing has to break into the gas phase, it can only do that from this top layer, right? It can't, like this guy can't go into the gas phase. There's too much stuff in the way. So you need to take off from this top layer. Think of every position in this top layer as a doorway, like out of this room, right? If some of those positions are taken up by solute particles, that's just less places that your solvent can escape into the gas phase from. So either which way you cut it, it's probably a combination of both those things. Those are both like solid theories. The vapor pressure of your solution is always going to be lower than that of the pure solvent, right? Because there's less particles escaping into the gas phase. All right, let's do boiling point elevation, freezing point depression. So kind of do these simultaneously. So you're looking at a phase diagram here. All right, this black line is the pure solvent. All right, so if I add something to my pure solvent and make a solution, right? all of a sudden I get these blue lines, right? So these change, our freezing point changes, our boiling point changes. Like, why does this change? So think about what's going on when you have something boiling. That's when the vapor pressure, so the boiling point is where the vapor pressure equals atmospheric pressure. So if you lower the vapor pressure by putting something in, right, that means you have to heat it up even hotter to get it to boil. So that difference here, this is our change in the boiling point. This is our boiling point elevation, this delta TB, right? Kind of the same thing happens on the other side, right? When the stuff's trying to freeze, if there's a solute in there, it's getting in the way. It's just kind of monkeying things up. It's the monkey wrench in the works, right? It has a hard time freezing when there's that solute in there, so that lowers the freezing point. And so that difference, that's delta TF. That's the change in the freezing point. This is why they salt roads in the winter, right? They throw salt all over the roads to lower the freezing point because salty water is a lot less slippery than ice. The amount that these things change, just think about it for like half a second here. It depends on how much stuff you put in there. If I only put in a little bit of solute, this only changes a little bit. If I put in a lot, it changes a lot. So it's proportional to how much stuff you put in there. So let's get to the actual equation because this has an equation. All right, so this is the boiling point elevation equation. So delta TB equals KB times little m. This is molality, right? Moles of solute divided by kilogram of solvent. All right, this is the change in the boiling point. This is a constant, right? This is the molal boiling point elevation constant. It is a property of the solvents. All these different things have a different KB, so different solvents will have a different KB. The thing I really want to point out is that this tells you the change in the boiling point. This triangle thing here, this is delta. You may have seen it before, right? It means change in the boiling point. So if I have an aqueous solution and I'm doing this calculation and I solve it and it says delta T is 3 degrees, right? That does not mean that the boiling point of my solution is 3 degrees, right? That means the change in the boiling point was 3 degrees. So what I have to do is add 3 degrees to the normal boiling point of our pure solvent. And so if I was doing this in aqueous solution, the normal boiling point of water is 100 degrees. So the boiling point of the solution would be 103 degrees for that example. Cool? All right, so just make sure you do that because you'd be surprised at how often I will see people saying, you know, here's my boiling point, and it's like 1 degree or something crazy like that. It's like, no. That was the change in the boiling point. All right, so this is the change in the boiling point. The freezing point, it's the same equation. All right, so the change in the freezing point, only it's a freezing point depression. So this is how much you will subtract from the normal freezing point. And the other thing I want to point out is that KB and KF, they are different. I mean, not just because, it's boiling and freezing, but even with water, KB for water is 0.51, KF for water is 1.86, and the units on it are degrees Celsius per molal. So when you multiply it through, you get degrees Celsius, all right? One last little thing here. All right, kind of getting back to the ionic compounds versus molecular compounds. There's something I like to call the X factor. It's actually the limiting value of the Van 't Hoff factor. That's the real name of for this thing, but we're just using the limiting value. But we need to modify our equations here, our boiling point elevation and our freezing point depression, because, well, not all things pack the same punch. If I have a molecular compound, right, so what I do is I put in this X, right, this X factor. This tells me how many particles that 1 mole of the stuff breaks up into. So how many particles do I get per mole of solute? All right, so if I have a molecular compound, if I have sucrose, if I put in 1 mole of sucrose, I get 1 mole of sucrose molecules, glucose, methanol, caffeine, whatever. They're all molecular, all right? The X factor would be 1, because for every mole of that stuff I put in, I get a mole of particles. It's the ionic compounds where things get gnarly here. Look at this craziness. All right, sodium chloride. When you put sodium chloride into water, you get 2 moles, right? So 1 mole of this makes 2 moles of particles. 1 mole of sodium, 1 mole of chloride. If I did magnesium bromide, that would give me 3 moles of particles, right? Because you have magnesium and then 2 bromines for a grand total of 3. If I had 1 mole of iron 3 iodide, dissolve that in water, I actually would have 4 moles of particles. And so just remember, all these colligative properties, they depend on the number of particles. So this is like the moles of particles divided by kilogram of solvent, right? So it doesn't care if they're not all the same thing. That's no big deal. These colligative properties, they don't mind. All right, so just don't forget that X factor. and all will be good. All right, catch you in the next one.